Fluid flow through porous media takes place in a wide range of systems. Let's consider, for example, our bodies. We have veins and arteries carrying the blood, as well as air coming into our lungs and exhaling CO2 and nitrogen. At the same time, we have a pumping system, which is our heart, and we have a cleaning system, let's say our kidneys. So we see the importance of fluid flow in our bodies. Similarly, we can anticipate the importance of fluids in soils, both for near-surface geotechnical engineering applications, as well as for deep formations in the context of energy resources, for example. Classical studies of fluid flow start with hydrostatic conditions. In other words, there is zero velocity, the flow velocity is zero, and the system is under equilibrium conditions. There are no changes in time. Now, it is possible that the system is in equilibrium as well under steady state seepage. But now the fluid velocity is not zero, and the fluid pressure is changing spatially to take into consideration flow conditions. But once again, in this case, the velocity remains constant, therefore there are no accelerations, and if we observe the process now or in a year, it will be exactly the same. The third situation is a transient. Imagine that you jump on a sponge filled with water, and you're going to hear the water squishing out of the sponge and changing in time, while at the same time you contract the sponge. So this is a typical case of pressure diffusion. In other words, the fluid pressure varying in time. And this is what we are going to call typical consolidation. In the geotechnical engineering community, please be careful, because consolidation has a different meaning in other fields. Like for example, a consolidated material for petroleum engineering is a cemented material, a cemented sand. So these are our three basic situations with fluids in pores, but the story gets rapidly more complex. For example, we could have air and water, like we have in our lungs, and this leads to partially saturated soils. It is very relevant to the migration of contaminants, L-NAPLs and D-NAPLs, to resource recovery, gas and petroleum, and for the storage, for example, of CO2 for geological storage, or hydrogen in the hydrogen economy. The same way as our blood leaves oxygen as it travels through arteries and picks up CO2 as it comes back on veins, this is a form of reactive transport. The fluid is interacting with the matrix that is traveling through. Fluids are continuously reacting with our mineral that creates the host. And then we have to wonder what will be the effect on granular materials like soils when grains gradually dissolve. We do know that acid rain or rain in general, as it goes into carbonates, gradually creates larger and larger cavities, the typical example of karst terrains. But we do not need to reach to some extreme condition to see important implications of reactive fluid flow. That goes from sands dissolving all the way to clays reacting with the invading fluids and changing the thickness of the double layer, whether the invading fluid has high ionic concentration or very low ionic concentration. Finally, we have to wonder about the different sources of fluid pressure, because we have the hydrostatic fluid pressure, we have the fluid pressure that comes from a steady state seepage, we have the excess fluid pressure for this transient, and then there are fluid pressure both for the two immiscible phases, the liquid and the gas, let's say, air and water. So U air and U water. And reactive transport, where the soil contracts, can also create an excess pore pressure. But if you remember, effective stress is sigma minus U, and the strength is equal to, the ultimate strength is equal sigma effective tangent phi according to Terzaghi and Coulomb. And then we have to go back and understand what is the interplay between all these different sources of fluid pressure on the macro scale mechanical response of the soil mass. On top of all this, there are important material parameters that are involved. For example, if there is hydrostatic, we have the mass density or the unit weight of the water. If there is a steady state seepage, clearly viscosity becomes important. In transient conditions, because it's a diffusion process, it's the pressure diffusion, which in this context we are going to call it the coefficient of consolidation. In immiscible fluid flows, we're going to have the surface tension, the contact angle, and that leads to the soil-water characteristic curve. And in reactive fluid transport, there's some form of a reactivity coefficient. So many parameters emerge, and here is not only the viscosity, but also the permeability of the soil. And we need to understand how to measure them, any type of databases that we can use to corroborate our measurements and anticipate behavior. This is the context of this section. Come and enjoy.